cos theta d theta, square that, and, well, dz squared, all right? So lo and behold, the metric here is d theta squared plus dz squared. Therefore, the cylinder is what? It's flat. Why?
Because that is the plane metric.
That's right.
The plane of theta and z.
That's right. If I use theta z coordinates on the cylinder, the components are the Kronecker delta, ij, with respect to 2 dimensions. So the cylinder's flat. Now, it's not isometric to the plane, right? Because there is no one-to-one onto bijection, right? There's no one-to-one onto map from the cylinder to the plane, because the cylinder has a different topology, right? You can't find a diffeomorphism from the cylinder to the plane. Every diffeomorphism is automatically a homeomorphism, because diffeomorphism is more. It's smooth, and smooth automatically implies continuous, right? So
is the cylinder closed?
yeah.
Is that why?
Well, I don't know if it's,
Well, I guess you know.
it's well, in what sense?
I realized since I was talking about when it matters.
I mean, every subspace is both open and closed with respect to the subspace topology. These are words that you should have heard this week.
Yeah.
Yes. Sometimes Dr. Skambordis is very discontent with things being both open and closed. He gets kind of irate about it if you can get him going on it. Yeah, it's funny. Oh, check this out. So example 7. This is one of note. So G circle on top is that horrible map. Pull back G bar. Where here, that horrible map is the mapping from the end sphere. I can't make this stupid circled thing. Back up. Sn into Rn plus 1, right? And this is the so-called round metric, aka standard metric. On the sphere.
What about to show that it's flat?
The sphere is flat?
The round metric is flat.
No, it's not. It's not.
Which metric has the highest k constant?
The highest what?
In complex last year, you said the k constant was
Curvature.
Oh, the curvature. Yeah, we'll get back. We'll get back to that. We'll get back to that. But
Will we actually get back to that?
yeah,
Ooh.
but not in this book.
Okay.
I'm changing books again. So, but not really. I'm just going to show you guys stuff. So, I guess my question is, what does that actually look like? Like, can we calculate this thing? So just to give you a snapshot of the rest of this section, like the next thing he does is he develops for a graph, what is the metric on a graph? So like a graph is a subset of Euclidean space, right? So you can pull back the G-bar, right? You can find the induced metric on the graph, and he finds that. And then he spends about 2 pages deriving a flatness condition for a surface of revolution. So like a surface of revolution is a particular kind of, it's got very special formulas. So that's pretty cool. The other way we could have gone with this example, by the way, would have been to notice that you could look at like partial z and partial theta, and you could prove that those are 0. Like I could have, I wouldn't have given it as partial theta. I could have found the tangent field, the radial tangent field, basically. Not radial, but the tangential tangent field. Oh, that sounds dumb. The tangent field that wraps around the cylinder if we could have found the formula for that in xy coordinates, you could have shown that that commutes with the tangent vector field to this way. If I wave my hands enough, it'll make sense. So, but I'm actually really happy with this calculation. So I'm at peace with that. See, this is interesting, right? This looks wonderful, but how do you actually calculate that, you know? What does that mean? Ooh, maybe I should use ones, yeah? I'm going to put the lower one just because it's annoying to put it upper here. But in your mind, think of them as upper. Oh, fine! Son of a gun.
Too much of a perfectionist to let it go.
It's just, the thing is, the later part of this section is about the musical morphisms, and their up-down indices means the world. All right, so what on earth are musical morphisms? Well, I'll tell you in a second here.
You know why it has sharps and flats?
Yes, it is. Isn't it horrible?
I saw that in the appendix too.
I'm all for it. I'm excited for that.
So, okay, so if we were to use, for instance, one way you could go here is you could be like, I'm going to use x1 through xn for coordinates, and then my xn plus 1 is xn plus 1 squared would be 1 minus the rest of them. You know? And if you believe in the calculus here, then I guess that must mean that 2xn plus 1 dxn plus 1 should be equal to, minus the sum I equals 1 to n of 2x upper I dxi, right? And then you could just, oh, ew. I just don't know. I don't know, guys. Like, I'm not sure. I wish I had an hour to calculate this before class, but I haven't. So let me stop talking about it. I'm a little bit, I'm not sure what's the right way to find formula for this thing. Yeah? One way I'm thinking about is, remember that problem? I worked out the parameterization of the n sphere with my souped up hyper spherical coordinates. So basically you could differentiate those and square them and add them together, and that would give you the formula. Just like we did for the polar coordinates. So like, for instance, oh, you know what, let's make it easier. So n equals 3. You have x equals to r sine theta sine phi, right? Y equals to r cosine theta sine phi. Z equals to r cos phi, right? So you could take these, and these of course define a what? These parameterize the two sphere, right? These give you a patch on the two sphere. So like x of phi theta is an element of the two sphere, radius r, right? And if you were to calculate dx squared plus dy squared plus dz squared, pull back, yes, pull back of that under my parameterization map, right? That would give me a formula for the round metric on the two sphere of radius r. And I can tell you what happens. So this ends up giving you a minus sine phi squared. This one, the dz squared, gives you a sine squared phi. These, when you square them, they give you they give you two things. On the one hand, from the differentials with respect to phi, they give you sine squared plus cosine squared, both of them packaged with a cosine phi. That adds together to give you r squared cosine squared phi. But that r squared cosine squared phi adds together with the sine squared phi to give you a net of r squared d phi. And then the theta derivatives, if you can use your imagination, the theta derivatives in the dx and the dy, those give you a r cosine theta sine phi and a minus r sine theta sine phi. When you square those, you pick up a plus r squared sine squared phi d theta squared. And so there you go. That's the formula for the round metric on a sphere of radius r in R3. And you could derive the formulas for the round metric in R4 for the 3 sphere using my horrible parameterization for the n sphere that I gave you guys in the homework. It's just a matter of differentiating, squaring, and adding stuff together. Thankfully, the cross terms be canceling because these are an orthonormal patch. Like the variables are, it's nice. The thing that happened in the earlier example where the cross terms didn't cancel doesn't happen for this. There's a technical term for this, but I don't remember it.
I have to go.
You gotta go? Oh, is it time? Man. I'll stop. I guess no musical morphisms today.
I'm excited for the musical.
Womp, womp, womp. Yeah.
I don't know what